Let's face it, transport phenomena is not an easy subject. And I remember as an undergrad, I really used to feel intimidated, all those huge equation in momentum transport. And I thought I will explain this video using an exemplar, which will be this particular problem, which I'll be sharing with you soon. And this problem was given to me as an assignment in my undergrad, masters, as well as my PhD course. So I think this is a favorite of all transport phenomena professors. And as long as you understand this, I won't tell them. Alright, so let's get started. So I was speaking about this particular problem, which is the flow in an annulus. I'll give you a couple of seconds to read this question. You analyze this, think about it, and then get back and continue this video. So I'm giving you a couple of seconds. Okay, so yeah, so this is from Bird Stewart Lightfoot and BSL, and it's in chapter 2, problem number B7. And this is how the problem goes. In essence, we have a rod which moves through this particular annulus, and the modified pressure across each ends is kept at a constant level, and we need to find the velocity distribution in the narrow angular region, right? So if you're new at transport phenomena and you're not understanding Navier-Stokes equation, that's totally fine. I'm hoping to get the message across using this video, and I hope I do a good job at it. And you better write down notes, because I think this will serve as a good exemplar to operate Navier-Stokes equation in a cylindrical coordinate. So you can see evidently it's a cylindrical coordinate because our object is cylindrical, duh. But yeah, so the first step will be to look at the givens and assumption. So we will see what all are given and what assumptions we can make. So we have the rod of radius kappa r, which moves at a velocity of v naught axially through the annulus, that's given. Again, the pressure drop is maintained as delta P equals 0. We have Newtonian fluid, we have the fluid is incompressible, all this is given in the question, and we have laminar flow. So laminar flow will make our life simpler, because if it's not laminar flow, we cannot apply Navier-Stokes equation, which will make our life very difficult. Newtonian fluid basically implies that the viscosity is constant and doesn't change with respect to time, and we have the fluid is incompressible, so the density is constant and doesn't change with respect to time. So all these assumptions make our life simpler and easier for us to compute the final value of this problem. And obviously we'll again ignore edge effects, another assumption which will make our life simpler. Okay, so step 2. So we need to identify what's the nature of the velocity. So what I'm basically trying to say is we need to identify which velocities are 0 and which one is not. And in this particular problem, it is clear that v theta and vr are 0 in the cylindrical coordinate, and we are calling it equation 1 and equation 2, right? And we have vz. I'll call it vz, but in some countries like the United States they call it z, but I've been using z all my life, so make note of that. And yeah, so vz is a function of r, theta, z, and t. Now it cannot be a function of t in this case, because we've already been given that it's a steady state condition. So we are analyzing the system when t tends to infinity, right? There are no dynamics as such in this system, and it's not a function of theta due to symmetry. You can argue that it's due to symmetry, or there's another interpretation to this. Recall that the shear stress is transferred to a plane perpendicular to the velocity component, right? So imagine there is some momentum across theta, but there is no boundary around theta, right? So that would imply that shear stress will keep on, you know, increasing around theta, and it will finally tend to infinity because shear stress is obviously force per unit area. And so Vz won't be a function of theta because that case is not possible. So if you didn't understand what I just said, just recognize that theta is this is a 2D structure, and we will not consider theta. That's it. And yeah, so we'll recognize that Vz is only a function of r and z. So that's equation 3. And this is a figure of someone who did a computational fluid dynamics analysis of this particular question. I didn't do it, I got it from the internet, but this is what it will look like, right? Okay, so step 3 will be the equation of continuity. So equation of continuity is basically mass balance, and you can derive it through several ways. I think in the book Bird Stewart Lightfoot, they have used a cube and tried to do mass balance. We can even use Gauss divergence theorem to derive this for a general case. Yeah, all that was unnecessary information, but anyways, so we'll take a look at equation of continuity and try to get some inference from the equation of continuity. Okay, so we can see that I have written down the same thing here. This is the equation of continuity in cylindrical coordinates. We know that the fluid is incompressible, and the density doesn't change with respect to time, so it's 0. We have already identified that the r component of velocity is 0, so this entire term becomes 0. We know that the theta component is 0, so again this entire term becomes 0, which leaves us with this particular component. And we know that the density is constant, so we can get that out of the partial derivative. And finally we can see that Vz is dou Vz by dou Z of this particular partial derivative is equal to 0. And guess what? This implies that Vz is not a function of z at all through equation of continuity, because if this particular case is true, that means Vz was not a function of z in the first place. And equation of continuity signifies the mass balance, and mass balance is always true in our problems. So we can now infer that Vz is only a function of r. So this is equation 4. I hope that's clear. If not, you can always write your feedback in the or questions in the comment section below, and I'll be very happy to answer them. Okay, now comes step 4, right? This is the scary looking equation which I personally dreaded during my undergraduate course, but this is not too scary after I explain it to you, right? So equation of motion has a really long and tedious derivation. I won't be doing that ever, so please don't request me to do it. So we will see that the first two equation of our Navier-Stokes equation will be redundant. Why? Well, I'll show you why. So we will write equation in R. We know that R is 0, so these terms will get cancelled. These are 0 basically, and we will see that this entire side will become 0, right? And again, when we look at the right hand side of this equation, we will again see that this term is 0 because Vr is 0, we know that. So everything becomes 0 here in this bracket, and this leaves us with the modified pressure, which doesn't give us too much information, to be honest. And what do we need to find? We need to find the velocity profile of Vz, right? So doesn't help us. And again, equation of theta will again be 0, and this doesn't give us any information as such about the velocity profile within the annulus. So we shift our attention to the z coordinate of this equation of motion. So let's look at this equation now. So we will see that dou Vz by dou t is 0 because of the steady state assumption. It doesn't change with respect to time. Vr is 0, we have already established that. V theta is 0, we have already established that. And from equation of continuity we know that Vz is not a function of z, so this term becomes 0. So this leaves us with the right hand side, and we know that again Vz is not a function of theta because of the two-dimensional assumption, right? We are only looking at the 2D structure, and we do not care what goes on with the theta direction. And again Vz is not a function of z, so again this becomes 0. So what this leaves us with is this particular equation. So now I have combined the pressure drop with the gravitation term, and when we combine these two, it's called as the modified pressure, right? And it's already been given in the question that the system is maintained such that the modified pressure across each of the rod is equal to 0, right? So the difference between them is 0, and hence this particular term will become 0, and it leaves us with only this particular term, and we know that it's 0. So we finally have this equation here, and this is equal to 0, and we know that mu, which is our viscosity, is a constant, and r cannot be 0, so we can just get rid of it, which would imply that this particular equation is 0. Okay, so now comes the tricky part, right? So since Vz is only a function of r, the partial derivative is equal to the derivative with respect to r. So we are basically converting our partial differential equation into an ordinary differential equation, which again makes our life very simple. So it is valid to change those doughs into d, and we have an ordinary differential equation here, right? So you can't always do that, so you need to see whose function Vz is of, right? Or else this equation won't be valid at all. So we will integrate once. We have C1 on the right hand side, and we'll integrate it again to get this equation, and we'll call it equation 5. And yeah, so now we have two unknowns here, which is constants of integration C1 and C2. And in order to find these constants of integration, we need at least two values of this function at whatever points, and luckily for us we have something called as the boundary conditions. Okay, so step 5 would be to apply boundary conditions, and in terms of boundary condition we have something called as the no slip condition, right? So the velocity of the fluid is equal to the velocity of the body it is in contact with. So that's how I would define no slip boundary condition, and that's my personal definition. Don't quote me on it, but I think that's about it. This is what no slip boundary condition means. So what does that mean? So at r is equal to kappa r, so this is equal to kappa r, right? The fluid is in direct contact with the moving cylinder, and Vz will be equal to V0. The axial velocity of the fluid will be equal to the velocity of the cylinder. And similarly, at r equals to capital R, which is this one, the velocity of the fluid will be 0 because the cylinder is stationary. So step 6 will solve for integration constants, And yeah, so we'll solve for integration constants, and we'll apply boundary condition 1 on equation 5. We'll get this, and we'll again apply boundary condition 2 on equation 5, and we'll get these two equations, equation 6 and 7. These are two equations, and we have two unknowns, so we have degree of freedom 0, and we will be able to find our values for C1 and C2. So we will get the value of C1 as this. Please solve them by yourself and verify whether I have given you the correct answer or not. And while C2 is equal to this equation. So we will substitute these two, equation 8 back in equation 5, which is the ones with the unknowns, and finally obtain Vz. So yeah, so this is our final answer. So if you have any questions, please do comment and we'll answer them. And that's it, that's the answer. And if you want, you can wait for some more time for a bonus round. We'll try to visualize this on MS Excel. Oh hey guys, you hung around. It's really good to see such enthusiastic viewers, and in order to understand better, I think it's good to visualize whatever answer we have got. And we'll put this on MS Excel now. So just for our convenience, I'll just copy this and paste it here, right? And yeah, what are the constants here? We have V0, which is a constant. We can just assume it to be 1, right? So this will be 1 meter per second. And we can have kappa, which will be equal to say 0.1. Anything between 0 and 1, other than 0 and 1 is fine, right? And this won't have any unit, it's dimensionless. And let's define r, the radius of the annulus, as 1 meter, and it's 1 meter, right? And since we have ln k in our denominator of our equation here, we will just compute this, but in this case it will be 0.1, but we'll try to vary it. So we'll just write ln k equals log of this, right? So right now its log will be equal to -1, and now we will write different values of small r. So small r will range from 0, 0.2, so on up to capital R. So we'll just extend this particular just extend this particular thing and until 1, right? These are the valid values, and we need to find Vz, right? So Vz will be equal to V0, which is this, divided by ln k, right? Just making sure everything is in the bracket, into log of r divided by r. So this will be small r divided by capital R, which is this, which is the total radius. And yeah, another thing is we'll make these cells constant, the ones which are supposed to be. Oh man, what have I done? Why? Just a second. So everything is fine. So right, so we will write this as a constant. So I'll just do function f4, put those dollar signs in. Again, this will be a dollar sign, this won't be a dollar sign because this r will be varying, and finally b3 will again be a dollar sign because it's going to be a constant. So it's not defined at r equals 0, we can see here, right? But when we extend this, we will see that wait a minute, 0.1. Yeah, so we can see that the velocity will be 1 meter per second at kappa r, which is 0.1, right? Kappa into r will be 0.1, 0.1 into 1. So that will be equal to the velocity of our fluid at the boundary of our cylinder, while at the edge of the annulus we'll have velocity will be equal to 0. Now let's vary it, right? We'll vary kappa, so let's write 0.2. So now we can see that so this is theoretically inside the annulus, right? So if the annulus was say hollow, I think this is what it would look like, the velocity within the cylinder rather. And we can see at 0.2 we'll have again maximum velocity, and it will range up to 0. So these two cases won't be valid in our case because our cylinder is a block. Well, I hope you guys understood how to solve this question, and I do know it's not an easy subject at all. And if you have any queries, you can always comment down in the comment section below, and you can also email us at cheme.friends@gmail.com. The links in the description box below. Don't forget to follow our Instagram page, and until then, take care. Bye.